Today being our last class, I think it'd be most useful to do a summary of all the topics from the class to remind you of things. You know, things are stored in the recesses of your brain somewhere, a couple cells here and there. We want to try to bring them to memory, in part because it might help you study, and in part because, well, it try to bring the course together as a whole. This is a summary of the topics that we've done in Calculus 2, right? It's worth doing, if nothing else, to just bring the course into mind as a complete unit. What did we start with? We started with a review of Calculus 1, at least the ending of Calculus 1, where you talk about integrals for the first time. You could say the fundamentals of integration was our first topic. And for us, that was what I also tested you on for the mini exam. And again, your final exam will include some modified problems from the mini exam, exam 1, exam 2, and some new problems about differential equations. The mini exam was about the fundamentals of integration. For example, we spent a lot of time talking about problems where you were given, say, a velocity, and you wanted to find the position. Given velocity, find position, or more generally, change in position. You might represent the change in position symbolically as a delta F, where we're using a capital F there because it's going to be an antiderivative. That would be your change in position. Change in position. From, say, sometime t equals A to some other time t equals B, oftentimes A is 0. Of course, we could just represent that as a difference, capital F of B minus capital F of A. But we said is conceptually, we motivated the computation of this in terms of the velocity as being an integral of the velocity. Capital F prime of t is the velocity. If the motion is one directional without going back and forth, maybe you're dropping a ball straight downward, you only go downward, then the change in position can also be thought of as distance traveled, and the velocity can be thought of as speed. But we want to allow for back and forth motion, either left and right, or maybe up and down. So we talk about change in position and velocity rather than distance traveled and speed, but you should be able to handle either way. We talked about estimating integrals with Riemann sums, and I'll come back to that. We also talked about interpreting these as areas. And if you've got the velocity, capital F prime of t, graphed as a function of time from t equals A, say right here, to some other time t equals B, say right here, then we talked about how you can interpret the integral, which is the change in position, as this area that gets shaded that way, minus this area that gets shaded that way. If I call this A1 and think of it as a positive area, and this is A2 and think of it as a positive area, the fact that that one's below the axis, meaning you're traveling in the negative direction, means it contributes to the integral negatively. The integral will equal A1 minus A2. And you can see I've made A2 smaller than A1. In a sense, you're traveling more in the positive direction, more enough to make that area bigger than this area. And that means your change in position is positive. This is a back and forth motion where, say, rightward motion is positive. You're going to the right, then you're going a little bit backwards, and your net change in position is smaller than your distance traveled. If I had made this area bigger, the graph is below the axis more, the motion is to the negative direction more, then your change in position could be negative. A2 could be bigger than A1, and this difference could be negative. So that's a conceptual approach. And it also can be generalized. Generalizes to any quantity that, say, depends on time, any quantity that depends on time. That's the most typical application, at least, is one that depends on time. Depends on time t. There are applications where the independent variable is not time, but the easiest applications to imagine are when it does involve time. Is the integral of its derivative, the integral of its rate of change. Rate of change of the quantity with respect to time. For example, I think the main other example we did here was imagining water flowing into a tank and, say, also draining out of the tank. The quantity of interest is the volume in whatever units you want to use, cubic meters, for example, cubic centimeters, or liters. And the rate of change with respect to time might be in, say, liters per minute or something. And if this graph were the graph not of the velocity, but of the flow rate, when it's positive, that means water's flowing into the tank faster than it's flowing out. Or maybe it's only flowing in from the top. And when it's negative, it's draining out faster than it's flowing in, or maybe it's only draining out. Once again, the integral, the difference of these two areas, gives you the change, in this case, of the volume. And there are plenty of other applications. Change in the amount of money in an account is the integral of the flow rate of money, the cash flow. And maybe, for a company as big as Amazon or something, it might be billions of dollars per day or something. Might be their cash flow, $2 billion a day. They want it to be positive. Of course, they got expenses too, so there's a negative cash flow too. And it's possible the positive cash flow of money coming in minus the cash flow of money going out could be negative, and they're losing money at a given time. Okay, so this generalizes to all sorts of situations. That was our first conceptual point. As far as doing integrals, that was the fundamental theorem of calculus. I mean, you could call this the fundamental theorem of calculus up here as well. Though in a sense, we were thinking of it more intuitively, almost as a definition. And down here, when we apply the FTC to do an integral like this, and let me change the variable name to be, say, x here, not that I have to. We've mostly been using calculus by doing integrals. And to do the integral, you've got to find an antiderivative, capital F, and do capital F of b minus capital F of a. We called that the first fundamental theorem of calculus, though many textbooks actually call it the second one, and I think that's actually a better label. But it is the one that's used more often. And so in that way, it's still an okay label. However, if you're going to use that, you've got to be able to figure out what capital F is. Here, it's more like you know the rate of change, and you're trying to find the function itself. Here, it's that you're trying to do the integral. That's what we use the most. But it's not always helpful, right? It's always true, as long as it turns out capital F exists. That's an antiderivative. But it's not always useful because you can't always find a formula for capital F. Thus, we need numerical integration sometimes. Because some integrals are just too hard to do. Or even, you might say, technically impossible to do symbolically. They're just too hard. The FTC2, which some books call FTC1, also tells us about the rate of change of integrals. Let me go back to using t here. When the variable is in the upper limit of the integral. If for a given function little f, we define a function, a new function, by integrating little f from some number a to a variable number t. And remember, it's a definitely good idea to use a different letter in here, like say a tau. You want to emphasize that the true variable for this function is that upper limit of the integral. That needs to match what you're differentiating with respect to. The variable you put here can be pretty much anything except letters you've already used. Don't use an A, don't use a D, don't use an F, don't use a T. You could use a tau, you could use a U, you could use a V, you could use a W. I talk about Xi. You could use a Xi. Did I talk about that? My favorite Greek letter. That one. Squiggle. Okay, yeah. Sometimes I put a squiggle there. Xi. Just because it's so beautiful. Use something different. Second fundamental theorem of calculus says when little f is a continuous function, this will be a differentiable function and its derivative will be little f. However, some people get confused here too, and they put, oh, I don't know, what should I put inside? Tau? No, put t. That needs to match. That needs to match that as well. These must match. It doesn't matter what the letter is that you use, just be consistent and put them in the right spots. For emphasis, sometimes I like to say, variable names don't matter. You could even name your variable treble clef or something. F of treble clef is treble clef squared. Partially because it's a beautiful symbol to make, and partially just because it just emphasizes variable names don't matter. It's the idea that matters. That's the squaring function. But you do want to be consistent sometimes. These must match. Also, with the fundamentals of integration, we did properties of integrals. Properties, can I spell properties? Properties of integrals. It is harder to spell, by the way, when you're teaching. I find, and it's weird. I don't know if you experience this. I find it a lot easier to spell correctly when I'm typing. I mean, yeah, I've got the spell check also telling me if I spelled it wrong. But even if I don't pay attention to that, I don't know, somehow I just naturally spell correctly when I'm typing. But I don't know so naturally spell correctly when I'm writing. It's weird. Properties of integration, including, for example, linearity. This came up on the mini exam. If you integrate, it's called a linear combination of functions, say some constant C1 times f of x, plus some other constant called C2 times g of x, that you can break that integral apart into two integrals and you can factor the constants out in front. It's kind of like a distributive property, you might say. Kinda. That's an example of a linearity property. And without a linearity property like that, calculus wouldn't be nearly so useful. This is actually super useful. In fact, in a sense, you use it all the time without thinking about it anytime you're integrating some sum of functions. Though it is possible to think of it purely in terms of FTC1 and just find your formula for your antiderivative without thinking about it. But sometimes that itself is a sum as well. So this is really a key property of integrals that makes calculus go. Other properties of integrals include what's called additivity. Let me show it to you in the book here for sake of time. Like this one, if C is some other number, then the integral of f from a to b is the integral of f from a to c plus the integral of f from c to b. That's most easy to interpret if c is between a and b, like it is in this picture right there, because what it's saying is the total area under the curve is the sum of these two other smaller areas. That's all it's saying. So it's easiest to interpret when the graph of f is above the axis and when c is between a and b. But it actually works even if your graph goes below the axis, and it also works even if c is, say, bigger than b. Though if you applied in that situation, technically speaking, you also need this fact, that the integral from b to a is the opposite of the integral from a to b. That's just there's nothing magical there. That's just a definition. Although the book's labeling it as a theorem, it's really more of a definition. Sometimes helpful. All this was on the mini exam. What else was on the mini exam? I think the idea of average value was on the mini exam. Interpreting average value. Approximating integrals, like if you given a graph and maybe you count boxes and find the area of each box and add them up. Remember doing problems like that? And or doing maybe a left and right hand sum to approximate the integral. I'll reemphasize those things in a minute. Before we do so, let's emphasize techniques of integration. Techniques of integration. Calculus 2 is all about integrals, doing them, approximating them, applying them, and then also stuff about sequences, series, Taylor series, and differential equations for the most part. Sometimes you work in polar coordinates. Sometimes you might work in a little multivariable calculus here and there. A little bit about vectors, which I try to do a little bit here and there. Techniques of integration, starting with substitution. Oh, say you're integrating x cubed e to the negative x to the fourth. Looks like a really hard integral to do, doesn't it? But just take a breath. Looks are a little deceiving. This is much easier than it looks. In fact, it's easy enough that if you've practiced this enough, you could even guess the answer. Because you look at that x cubed and say, hey, that's almost the derivative of, say, negative x to the fourth. I bet the answer involves e to the negative x to the fourth, plus perhaps, or put with some constant in front. And that's what you would guess, and you would be right if you guess such a thing. But you also, if there was x squared or x to the fourth or x to the fifth there, then it wouldn't be so easy. You also can make it a little bit more formal and actually do a substitution. U substitution or W substitution. Say W is negative x to the fourth. dW then is negative 4x cubed dx. Meaning x cubed dx can get replaced by negative 1/4 dW. So now I'll go ahead and make that substitution. Replace x cubed dx with negative 1/4 dW. Replace negative x to the fourth with w, you get negative 1/4 e to the w, dw. Which is easy to do, negative 1/4 e to the w plus c, but as an indefinite integral, don't forget to convert back to x, negative 1/4 e to the negative x to the fourth plus c. And you can always check your answer. And whenever you check your answer with substitution, you'll need the chain rule. But remember, you should also be able to do a definite integral with substitution. And in fact, it's the same substitution. And if you do so, and if you change the variable, I'm telling you, I'm picky about this, you must change the limits of integration. Yes, we can convert this to the integral of negative 1/4 e to the w dw. But if you're going to say these are equal, as definite integrals, you must change the limits of integration. Otherwise, they're technically not equal. And you use this equation, the substitution itself. When x is 2, w would be negative 2 to the fourth. 2 to the fourth is 16. It'd be a negative 16. This negative sign is understood, by the way, to be, in a sense, outside the x to the fourth. Do the x to the fourth first and then negate it. If I meant do the negative sign first, I'd use parentheses. And since fourth is an even power, you could actually ultimately get rid of the negative sign in that case. 3 to the fourth is 81. There's your definite integral that this equals. Notice negative 16, the bottom limit of integration, is bigger than negative 81. So a more common way to write this would be to switch the limits of integration around and change the sign of the negative 1/4 to a positive 1/4, and I'll go ahead and bring it out in front as well. And when you do it this way, you never have to go back to x. Just do this integral as is now. And you'll get 1/4 e to the negative 16 minus 1/4 e to the negative 81. Should be a really tiny number, really close to 0, but that is the exact answer. Okay. This function is really close to 0, evidently, because this integral is really close to 0. I might have you do it this way in the exam, and you must change the limits of integration if you want full credit. Some people get sloppy and they don't, and they get the right answer in the end. But I'm telling you, don't. Yes, your physics, chemistry teacher might let you be sloppy. They might say, all I care about is the answer. But I care about that you're writing correct things as well. Why? Because I'm nitpicky? Well, I guess in this context I am, because I think it's important to realize that to get equality, you must make that change. Next technique was integration by parts, IBP, which, here's a typical kind of example. Integrate, say, x times sine of 2x. If you're integrating a power of x times a sine or a cosine, or maybe e to some power, that's a common situation to use integration by parts. If the power of x is higher than 1, like x squared or x cubed, you might have to use integration by parts twice or 3 times. Would I do that to you? I don't think I did on the old exam. But in theory, realize if you need this technique in the future that you might have to, or use technology or use a table or something. And in this kind of situation, it is best to let u be x so that u prime is simpler. In general, the most important piece of advice about integration by parts is to make sure v prime is something in this product that is easy to integrate. Yes, sine of 2x is fairly easy to integrate. U prime is 1. V, the integral of sine of 2x, be careful, it's negative 1/2 cos 2x. I did an integral in my head right there. I integrated sine 2x in my head because of practice. I can do that in my head. I think it's always a good idea to write down the formula, u times v minus the integral of v times u prime, because by writing the formula, it reminds you of what it is every time, which you might need in the future to do things quickly, so you don't have to take the time to look things up. U times v is the product of the upper left thing and the lower right thing. That'll be negative 1/2 x cos 2x minus the integral of the product of the things on the bottom. 2 minus signs will make a plus. The 1/2 can come on front. And you're hoping that's an easier integral to do than the original, and it is. And you'll get, in the end here, plus 1/4 sine 2x. Don't forget your plus c. Whenever you check integration by parts problems, you need the product rule, because Integration by parts is really the reverse of the product rule. Substitution is the reverse of the chain rule. Integration by parts is the reverse of the product rule. If we were doing a definite integral here, do not change the limits of integration. And you might scratch your head and say, well, aren't there new variables here? Yeah, I mean, yeah, you could call those new variables, but we're not really using them in the same way as the substitution. We are still rewriting the integrals involving x, the original variables. Some integration by parts problems, you do not want to let the u be x. Or even say, if you were doing this example, you do not even want to let the u be 1 arctangent of x is 1 times arctangent of x. You'd want to let u be arctangent of x and let v prime equal 1. Because again, the most important thing about using integration by parts is that v prime is something easy to integrate. If I had let v prime be arctangent of x, to find v, I'd have to do the exact same problem I'm trying to do. That's no help. So it only makes sense to let arctangent be the u. It's not clear that it's going to be helpful, but you try it, and it is helpful. This integral right here can be done pretty easily, either by guessing or doing a substitution. W is 1 plus x squared. So dw is 2x dx. And x dx then is 1/2 dw. So we'd be doing minus the integral of 1/2 times 1 over w, dw. Integrating 1 over w gives you natural log of the absolute value of w. Replace w with 1 plus x squared. And I could write the answer this way. In general, you need the absolute value signs like you see here. But in this example, you actually don't, because when x is a real number, 1 plus x squared is positive. So I don't really need those absolute value signs there, but it doesn't hurt to keep them there. So to play it safe, you might as well. Make sense? Tracking with me here? Ask a question if you need to. Go ahead. This is simple enough that guessing is fine. Yeah. But again, it's only simple if you've practiced integration enough, right? Some of you might look at that and say, I don't know what to do. So then, yeah, try a substitution. But if you've practiced integrals enough, especially substitution problems, you get to a point where you recognize, oh, that would be a quick substitution, and you can guess the answer. But if that numerator was a 1, this would not be natural log. In fact, if that was a 1, there would be an arctangent. So it does depend on what the numerator is here in this example. And if the numerator were an x squared, instead of an x, you'd have to do long division first, actually. When you're integrating a rational function where the numerator has a degree greater than or equal to the degree of the denominator, you've got to use long division first before you do the integral. Would I put that on the test? I don't think I put it on old tests, long division, unless my memory is faulty. We did it in class. There were also problems I gave you where you had to use a table. If I don't remember if I put that in an old exam. If I did, I think I maybe gave you the table formula. Those tables are sometimes generated using integration by parts. Sometimes they're generated with trig identities. You should certainly know your trig identities, of course, and there's trig substitution as well. Trig sub is probably the integration techniques that involves integrals that are the hardest to do, yet we still did them. I don't want to go into a ton of detail there. you should practice kinds that we did. When you do the trig substitution integrals, you do need to use trigonometric identities as well. By the way, reminder, you can use a note card for the exam, but don't rely on it too much. Front and back. If I were you, I would not bother putting the trig identity you're most familiar with on your note card, cos squared x plus sine squared x equals 1, right? You should have used that hundreds of times in the past. You shouldn't need to put that in your note card. But other ones you might have to, because you might not remember them otherwise, or maybe I'd put these on the exam itself. I guess if I do, I will probably write the exam tomorrow morning. And if I do put these on there, I will probably give them to you and I'll let you know. Cos squared x is 1/2 plus 1/2 cos 2x. That's a useful one to do integrals of cos squared x, for example. Sine squared x is 1/2 minus 1/2 cos 2x. That's not a typo, that's correct. You can see by adding these two equations why cos squared x plus sine squared x equals 1, because these cancel. That's related to double angle formulas, in particular the one involving sine 2x is that it equals 2 sine x cos x. Yeah, I think why don't I just make that executive decision right now? If I put a problem and you need to put this on, use these on the exam, I'll give them to you. So you don't need to put them on your note card. I forgot to tell that to the first class. So I'll probably send a message to both classes that if you need that on your exam, I will give it to you. So don't bother putting these in the note card. But you got to understand when it's appropriate to use those. So trig substitution is different than just using these. You also have to do a substitution like x equals sine of theta or something. And then dx would be cos theta d theta. But in the end, when you convert back to x, you often have to use these things. By the way, these two here are definitely useful in multivariable calculus when you're doing what are called double integrals involving polar coordinates. These kinds of identities come up all the time. You have to use them if you're going to do integrals by hand, at least. Partial fractions is another one. And long division, though I think I didn't put that in old exams. Integrating rational functions. And I'd probably keep it simple. I did say to the other class, and I'm going to say to you now, it's possible I might put a gateway type problem on the exam too, where you just do an integral. I mean, I think there were some of those on exams, on the mini exam, exam 1 at least. But maybe I'd do another one where you just got to do an integral. Maybe not, but something you should be able to do. Of course, in many situations, no integration techniques are helpful at all. What's an example? Like integrating e to the x squared, for example. There's no integration technique from chapter 7 that's going to be helpful in doing that. You could try integration by parts, it's just not helpful. You could try substitution, it's just not helpful. In fact, somebody proved sometime, guessing 150 years ago or so, that it's impossible to do this integral in terms of elementary functions. What are elementary functions? Functions you're used to is a short answer to that. Polynomials, rational functions, square roots, cube roots, exponential functions, trig functions, inverse trig functions, logarithms, and finite combinations of all those things are called elementary functions. They're the functions you're used to. But there are plenty of other functions you're not used to. ERF, error function, gamma. What other ones do we see? Bessel, Fresnel, named after people who thought of them in the first place. There's other ones named after Jacobi, Legendre, probably Laplace, Euler. There are hundreds of other functions you've never heard of before that have very specialized uses. I think this one probably involves ERF. Doesn't mean it can't be done in other ways. You could represent this function as an infinite series and integrate term by term and write the answer as an infinite series. That's okay. It's not a finite combination of elementary functions, though. So the point is, when you're doing definite integrals in such situations, which, for example, comes up with a normal distribution and probability, you've got to use numerical integration, because the fundamental theorem of calculus is just not helpful. Numerical integration. You got to approximate the integral, not find it exactly. It's not that the fundamental theorem of calculus is wrong. Fundamental theorem of calculus is definitely true. It's not wrong. It's just not helpful, because you can't figure out what capital F is. That's why. So you have to numerically integrate, which is what technology does when it's having to do things like approximate definite integrals in this situation, is it's doing numerical integration. I'm not going to write down the formulas in summation form. I'll just remind you of the names. There's the left-hand rule and the right-hand rule. You break up your interval into subintervals of, say, equal length to keep it simple. Make all your approximating rectangles equal width, delta t or delta x. There's n of them. If you use the left endpoint in each interval to figure out the height of the rectangle, that's called the left-hand rule. Add up the areas of those rectangles. If you use the right endpoint, that's called the right-hand rule. There were things we saw related to whether these give you answers that are too big or too small based on whether your function is increasing or decreasing. You should briefly review. Better methods include the trapezoid rule and the midpoint rule. With the midpoint rule, we figure out the areas of our rectangles by taking the midpoint of each subinterval and using that to figure out the heights. And that generally does better than left and right. Trapezoid, for us at least, was the average of left and right. That's not the way it's defined in every calculus book, by the way. In many calculus books, the trapezoid rule is described in terms of areas of trapezoids right away. And the sum of the areas of those trapezoids is written down with the summation formula. It's not what our book does, because our book takes an approach of also thinking about the errors in numerical integration. Error is actual value minus approximate value. And it's convenient because that goes in alphabetical order, actual before approximate. That does tell you that if your approximation is too big, the error is actually negative. It's a little confusing, but that is the standard way to do it. And if the approximation is too small, the error is positive. What we typically see in most relatively simple examples is the error for the left-hand rule and the right-hand rule typically have opposite signs. One's positive, one's negative, with fairly simple examples at least. And they're also approximately the same size in absolute value, the same distance to zero. And therefore, it makes intuitive sense to average them. What we also see, if we think about the errors for the trapezoid midpoint rules in simple examples, is they tend to have opposite signs as well. And moreover, the absolute value of the error for the midpoint rule is typically twice as small, half as large as the absolute value of the error for the trapezoid rule. And the midpoint rule does typically about twice as well for any fixed value of n. And therefore, Simpson's rule for us is defined as a weighted average of mid and trap, where we give the midpoint rule 2 times the weight as the trapezoid rule. Effectively, we're counting the midpoint rule twice in this average. Since we're counting it twice, we had to divide by 3, not by 2. So called a weighted average. Right? We did all this. Also, you might say related to this is the fact that you could do integrals, technically speaking, as a limit as well. For example, if I have a definite integral like this, I could think of it as a limit as n goes to infinity of, for example, a right-hand sum, which I'll go ahead and write it out the summation now. I goes from 1 to n of f of xi times delta x, where delta x is b minus a over n, and xi is a plus I times delta x. So it's a little funny in a calculus class. We typically think of this as being a calculation tool, though it only is relatively convenient in only the simplest examples. Like maybe f of x is at most like an x squared function, a quadratic. And even then, I think we did an example or two, but we had to use Mathematica to help us because the summations were not so easy to figure out. And certainly in harder examples, if f of x is sine of x or something, or e to the x, trying to do it as a limit here is, well, it's pretty much impossible to do unless you quote unquote cheat and use the fundamental theorem of calculus to figure out the answer that way. On the other hand, you might think of this equation here as almost a definition of the integral, emphasizing that all of calculus is based on limits. That's what differentiates calculus from algebra, pun intended, differentiates calculus from algebra is limits, because limits is at the foundation of everything in calculus. Derivatives, integrals, infinite series, improper integrals, they're all based on limits. Is it really a definition? This is not quite good enough to be a definition, because to be a true definition, you have to be more general, because you would want not just the right-hand sums to converge to the integral, but you'd also want left-hand sums, you'd also want midpoint sums, and in fact, you'd also want even more general sums where maybe you don't use the left endpoint or the right endpoint or the midpoint, but some arbitrary point in each interval, and maybe you'd even want your rectangles to be varying in width. You'd still want the limit to be the same as the number of rectangles goes to infinity, or as all the rectangles get skinnier and skinnier. Does that really happen? Is the limit really the same? That's a very hard question. It can be answered, and it can be answered in the affirmative. Yes, it happens when your little f function is continuous, but that's a really hard thing to do. That's an advanced real analysis topic that only pure mathematicians typically have the stomach for. Though I will say, when I was in grad school, taking a pure math class like that, real analysis, that I had some classmates, one classmate in particular who was in grad school for accounting, and he had to take a real analysis class. So he had to trudge through it, even though he didn't like it. So you might have to, depending on what you do. An accounting PhD had to take real analysis. Actually, I talked to him about it. He's like, yeah, accounting PhDs are really more like economics PhDs. It's not really accounting in the usual sense of the word. Okay, what from there? Big break. On to applications. Calculus 2 is a very applied course. Maybe you don't feel that way, but we've really done what I would consider to be a ton of applications in here. To already mention velocity when you know position, or change in position when you know velocity, change in volume when you know flow rate, change in money when you know the cash flow. Imagine Amazon, right? Millions of dollars are flowing into and out of their accounts every second of every day. There's a cash flow going on over the internet all the time, every second of every day. And they could try to model their cash flow as a derivative of something, a rate of change. With a formula? Probably not a formula, it's probably numerical. I mean, yeah, they could approximate it with formulas, but over the long haul, it's probably just numerical data. But effectively, they integrate that numerical data to figure out the change in their bank account, you might say. Sure, they don't have their money all in one bank, though. That would be crazy. Anyway, of course, there are purely geometric applications. There's areas and volumes. And this is where we talked about the Riemann sums to help us figure out what integral to do. And the Riemann sums were just a hand-wavy kind of tool, right? Chop up the volume, the solid, into thin slices. Represent the volume approximately as a sum of areas of, for example, thin wafers whose cross sections are maybe circles, discs. Imagine adding those up and then say, hey, we don't really want to do a sum. We really want to do an integral. So now let delta x go to 0, let them all get skinnier and skinnier. And like magic, the Riemann sums turned into an integral. The delta x turned into a dx. That was just pretend for fun to say it's magic. It's not really magic. It really is just a definition. There's nothing magical about it. It only feels like magic. Of course, you could ask, is it a good definition? Does the volume I figure out of this solid by using calculus match the volume I'd get if I put this object in the bathtub and watched out how much the water raised? Somebody sometime must have done that experiment with some solid, okay? And yeah, they found it did work. Makes intuitive sense. These are really just definitions, hoping that they are definitions that make sense and are useful. To keep things simple, we did special cases for these volumes. Volumes of solids of revolution. I'll just write the word revolution here, where the cross sections are either disks or washers, which are ring shapes, or maybe cross sections where you're told the cross sections are maybe squares, equilateral triangles. That's the hardest example, or maybe semicircles. You know, the equilateral triangle example is the hardest because you got to use trigonometry or Pythagorean theorem at least. Also did arc length along a parametric curve, which I described more in terms of physics, like distance traveled along a parametric curve. You know, you had that exam problem where I had you draw a parametric curve using your calculator. I think it looked about like that. You had to write the speed as a function of time using the parametric equations and their derivatives. It also involved the square root. I also did have you do the integral by a substitution. There were very few people who got full credit on that one. By the way, that's worth studying. To tell you the truth, and I didn't know this in the first class either, I don't remember whether I had you draw the position and velocity vectors here. If I did in the past, and if I put this on the final exam, it's not too hard. Just do what I'm about to show you right now. The position vector, say at this moment in time, which we could pretend is t equals 2 or something, as we move along that curve. The position vector would be this arrow from the origin out to that point. That'd be the position vector. And the velocity vector, don't start it at the origin, start it at the point you're at. It's got to be tangent to the curve. So pointing in the direction of motion. Velocity vector. Technically speaking, if you're going to draw the velocity vector accurately, you'd also want to make its length equal to the speed at that moment in time. However, I think, more forgiving on that kind of thing during an exam in this class to not necessarily get the length correct, just after the correct direction, tangent to the curve, pointing in the direction of motion at that instant in time. Vectors are just used in brief places in this class here and there. More commonly used, of course, in physics. You'll also see them a lot if you take linear algebra or multivariable calculus or differential equations with linear algebra, a lot with vectors. We did briefly have some content about polar coordinates, polar graphs and areas. I didn't actually test you on it because I was gone the days I had you learning about that. That was right before spring break when I went out of town. And so I'd watch these old videos and do these homework problems, but I didn't test you on it. So I will not test you on it in the final. I might in the future class, if any future people watch this. Then we got into more physics applications, mass and center of mass. Simplest situation is with a thin rod. More complicated situation was when you got like a two-dimensional thin plate. You got to think about cross sections, say perpendicular to the x-axis. And the center of mass ends up being a ratio of two integrals. The bottom one giving you the mass, the top one giving you something called the moment. We also did apply this to other situations that are a little different, including, I think, on exam 2. We had a disc shape, and either that's the shape of some city and you're trying to find the population, or maybe it's like a compact disc or something, you're trying to find the mass, where the density is constant along circles centered at the origin. And you have to set up an integral for the mass in that situation by thinking about circles centered at the origin and thin circles. And effectively, the mass of the thin circle is the density at that radius times the approximate area of the thin circle that involves the circumference 2 pi r times dr, the width. That was on the last exam. Something where people did have some trouble with it. So that's something you should be able to do too. Work done by a force. Two main situations where you have to use calculus. One where you're pulling a rope or a chain up, the mass and the length is getting smaller. Another one, pumping water out of a pool. I think that was the one I tested you on. So if I put it on the final, that would be the type. There was also pressure on the side of a dam, for example, but I don't think I tested you on that one. There were also some finance applications here involving present value and future value. And I said that could have been on exam 2, but I don't think I tested you on it. Pretty sure I didn't test you on that. So I won't for your final either. But future classes I might for you. Actually, before the physics stuff, we also talked about probability, which I did test you on. probability we talked about PDFs and CDFs. PDF stands for probability density function. CDF stands for cumulative distribution function. Actually, probability density functions are very similar to physical density functions for thin rods. It's a very similar idea. Except with thin rods, you're thinking about an actual physical object, and you're actually imagining molecules on one part of the rod being denser than on the other part of the rod. With probability density functions, you're more thinking about data and how dense the data is. Maybe it's denser over here than it is over here, and the PDF you would create to model that would be higher where the data are denser and lower where the data are less dense. You want the PDF to integrate to 1, which is why when you compute the mean, you don't have to divide by the mass because it's 1, like we do for a center of mass of a thin rod. The mean is analogous to a center of mass. It's effectively a center of mass for the data that we're modeling. And you find percentages of the data, which can also be thought of as probabilities, by integrating PDFs. The area under the PDF above a certain range of values, like from A to B, gives you the percentage of the data values in there, if you got a lot of data at least, say at least 100 data points, which can also be thought of as a probability. The probability of your variable being between X and B, between A and B, is the integral of the PDF from A to B. And the CDF is just an antiderivative. It's a capital F. It's not any old antiderivative, though. And in particular, in our applications, our main application we thought about including on, I think it was either exam 1 or 2. It could have been exam 1. Was to wait times, like at an intersection. How long do you have to wait till the next car comes into the intersection? We used a probability density function that was an exponential decay, like that. And this is the little f of x, or little f of t, say. And in that situation, the variable t can't be negative. And you'd want your CDF to start to have a value of 0 when t is 0. The CDF would have a graph that goes to the origin in that situation. It would look like this. The smallest possible value of t, which is 0, has got to be the starting value, you might say, for the CDF. Capital F of 0 would have to be 0. You don't actually need that fact to do the integral. In fact, you could even have a plus c in the formula for the CDF and still do the integral because the plus c would cancel. But technically speaking, the CDF has to start there. And if we're in this situation, this kind of model, which is what came up on the exam, the mean is the integral of t times the PDF. And if it is this situation, where t can be any positive number, technically speaking, the integral is an improper integral from 0 to infinity. And to do it, you have to do a limit, right? Improper integrals there is what I'm talking about as well. Improper integral, which was technically, the improper integrals came at the end of chapter 7. These applications are in chapter 8. But the improper integrals, then when we talk about the abstract idea, was at the end of chapter 7. Integral. You should be able to do improper integrals as well for the exam, writing the limit sign as you do the calculation. It might converge, it might diverge. It depends on what the function is. Can I clarify anything there? those were our applications. Since then, there's still been more applications, I guess, but the topics kind of shifted from integration to sequences, series, Taylor series, and differential equations. Still, integrals were useful sometimes, though. Sequences and series is a big part of Calc 2. Oh, I only have 6 minutes here. Sequences, of course, can be defined directly or recursively. You know, here's a direct formula, for example, a to the n equals 2 to the n. Here's a recursive formula, a sub n equals 2 times a sub n minus 1, and say a sub 1 is 2. These actually define the exact same sequence. 2, 4, 8, 16, 32, 64. I'm doubling every time. More importantly, though, were series. The most common example of series was geometric series. Was our most common example. I could write a finite geometric series here, but right away I'm just going to go ahead and write an infinite one. And that converges as long as the absolute value of R is less than 1. You should, I didn't write down the finite one version. You should write that down probably for your note card, the finite geometric series as well. Then, that was sort of the motivation, the geometric series, but we also then talked about the definition of convergence and convergence test, right? If you've got an infinite series written either with plus dot dot dots or with a summation sign, you should know for a true false multiple choice question that this converges or not based on the corresponding sequence of partial sums. S1 equals A1, S2 equals A1 plus A2, S3 equals A1 plus A2 plus A3, etc. The definition of what we mean for the series to converge is that the sequence of partial sums converges. And if the sequence of partial sums does converge to some number as a sequence, like 10, for example, then we say the series converges to 10. It's as if we're pretending we've added up infinitely many things and gotten 10. We haven't literally done that. We haven't literally added up infinitely many things because nobody can literally do such a thing. But we're pretending. Why? Because it turns out to be useful, amazingly, to pretend to add up infinitely many things. It's useful. It's also, from a mathematician's perspective, just interesting to pretend. But in reality, we also have to think about convergence tests. Convergence / divergence tests. I have to go fast here. I'm just going to describe these verbally, but you should pay good attention. If the terms, the A's, go to 0, that doesn't necessarily mean the series converges. You need some other test. However, if you know the A's themselves don't go to 0, definitely the series diverges. That's called the divergence test. So that's the first one you should think about if the series is not obviously geometric or obviously some Taylor series. You should think about the divergence test. On the other hand, the more interesting situation is when the ANs do go to 0, like the harmonic series or P series in general. You know, that's a P series. And when P is positive, these terms do go to 0. But that doesn't mean the series converges. You know it converges when P is bigger than 1 and diverges when P is less than or equal to 1, which includes the harmonic series case when P equals 1. That's a fact to know. It can be confirmed with the integral test. But it's illustrating that just because the terms go to 0 doesn't mean the series converges. You need some other test. Integral test, comparison test, limit comparison test, ratio tests. Actually, the ratio test is not helpful with p-series because it gives you a limit of 1, which is the case where it gives no conclusion. It's most helpful when you've got factorials or 2 to the n, 3 to the n, that kind of thing involved. There was also the alternating series test. Then we moved on to power series, radius of convergence, interval of convergence, then on to Taylor series, which are power series, special power series, and tricks for calculating them. And then on to differential equations, the recent stuff. Make sure you work on old exam problems. I don't have keys, but you'll be able to see which ones you got full credit on and which ones you didn't. And I do typically try to make corrections if you made mistakes or make comments about how to do it. Practice those old ones with the video I shared on Wednesday. Practice those problems. I might also give you a simpler differential equation problem where I say, here's a function, here's the differential equation. Is this function a solution or not? You have to show work to check that it either is a solution or not. And then there's those models, Newton's law of cooling, exponential growth, logistic model, predator prey. Those are the main ones we did. Mass on a spring too, I guess. Okay. Thanks for being in the class. We'll see you on Thursday.